Today we start the second lecture on the scalar and vectors. In my last lecture, we have discussed about the scalar quantity and the vector quantity, as well as the types of vector and the addition procedure of vector. And also we discuss about the vector representation. In this lecture, we actually discuss about the vector representation for 3D case. 3D case means is a three-dimensional case, and we also discuss about the dot product, cross product, and the moment of a force about a point and about a line. Now you see here actually one force here, Cartesian coordinate system is shown here, and a force F acts from O to A point. If this force makes an angle with the x direction and the angle is theta x, then the component of this F in x direction, that is Fx, is equal to F cos theta x, where this F is the magnitude of the total force. If we multiply this magnitude of the total force with cos theta x, then we get the Fx, and this Fx is the component of this force F in x direction. And similarly, if this force F makes angle theta y with the y direction, then this is your Fy. Fy means the component of force F in y direction. Similarly, we get the Fz, that is the component of force F in z direction. Therefore, for a 3D space, when a force vector acts, we can represent this force vector F in this way, that is F vector is equal to Fxi plus Fyj plus Fzk, where this I, j and k is actually the unit vector along x, y and z direction respectively. If we put the value of Fx, Fy and Fz in this equation, then we get F vector is equal to F. F is the magnitude of the total force F cos theta xi plus F cos theta y j plus F cos theta z k. And we can write, if we write the force vector in this way, that force vector F is equal to F, the magnitude of the force, and this one is a lambda, where this lambda is also a unit vector along the F direction, along the direction which the force acts. Basically, for this case, force acts from O to A. If we multiply the magnitude of the force with the unit vector which acts along this OA, then we get the force vector. Okay. Then, therefore, from this previous equation, we can write that the lambda is equal to cos theta xi plus cos theta yj plus cos theta zk. Okay. Now, if we consider a force which acts from this M point to N point, and the coordinate of M and N is given here with respect to this Cartesian coordinate, that is xyz coordinate, and if the coordinate of M is x1 y1 z1 and the coordinate of n is x2 y2 and z2, and here you can see the force is acts from M point to N point, that is why arrowhead is towards N point. Then we can represent this force vector F, that is equal to force vector is equal to the magnitude of the force into the multiplied with the unit vector which acts along this M to N point. And we can write this unit vector lambda with respect to this equation, that is lambda, it is arrowhead is there, suppose we give here the arrowhead, okay, that is lambda is the unit vector which acts along M to N direction. Then we can write the lambda is equal to x2 minus x1 I plus y2 minus y1 j plus z2 minus z1 k, where this one is the upper one is the actually the position vector with respect to M to N. If we divide this position vector with respect to the magnitude of this vector, the position vector, then we get the unit vector, that is lambda. That is why it is root over x2 minus x1 square plus y2 minus y1 square plus z2 minus z1 square. Then from this equation we can actually find out any unit vector if we know the coordinate of the 2 point which is situated on the line of action of any force vector or any kind of vector. Okay, if we know the coordinate of any 2 point within the line of action of the force, then we can find out the unit vector using this relation. Okay, and if the magnitude and the unit vector is known to us, then we can write the vector. Okay, now after doing this problem, we can actually find the better understanding with the how we can find out the angle and how we can represent the force in 3D space. Okay, now in this problem a tower is here, the height of the tower is 80 meter and which is connected by the wire which is actually attached at point A, and the tension in the wire is given, that is 2500 Newton. Now you have to calculate the Fx, Fy, Fz, the force component at A, at bolt A, and if we consider the force distribution with respect to this A point, then the tension force will act from A to B, okay, and you have to also find out the theta x, theta y and theta z, the angle which is made by the force with respect to x, y and z direction. Okay. Now if we consider this point as the origin point, suppose we write here the coordinate point, and for this point we can write it is 0, 0, 0. Then for B point, what is the coordinate? For B point it is 0, comma, it is 80 in y direction, okay, and in z direction it is also 0. Then for a point the coordinate is from this point to this point, the displacement in x direction is 40. That's why it is 40, comma. In y direction the displacement is 0. That is why here it is 0. And in z direction, in this direction z is positive, in this direction z is negative. That is why it is minus 30. Okay. Now once you identify the coordinate of each point, then we can find out the unit vector which acts from this A to B point. Okay. Then the position vector from A to B, the position vector is, that is, we get from x2 minus x1. Here this one is x1 and this one is x2, because this is the final point. Force acts from A to B, that is why it is x2 y2 z2, and this is x1 y1 z1. That is why for AB vector we can write that is x2 minus x1, that is why it is minus 40 I plus y2, that is 80, minus y1, that is 0, that is why it is plus 80j, plus z2 minus z1k. Here z2 is 0 and z1 is minus 30, that is why it is z2 minus z1, that is becomes positive 30k. And the magnitude of this AB vector is this one. Okay. Once you divide the position vector by the magnitude of the position vector, then you get the unit vector which acts along this A to B point. Okay. Then we get this unit vector which acts along this A to B point. Now from the previous relation what we discussed earlier, we can write that the force vector is equal to magnitude of the force multiplied with the unit vector. The magnitude of the force is given, that is 2500 Newton. Then automatically from this equation we can write that is F vector is equal to minus 1060I plus 2120J plus 695K. Similarly, we can write that this, the coefficient of I, actually the Fx, because we can write that force vector, we can write this thing, that is force vector is equal to Fx I. Fx is the component along x direction plus Fy z plus fzk. Okay, then we can write this uh, this one, the coefficient of I is actually Fx, that is the force component along x direction, and this one 2120 is actually Fy, and 795 is actually Fz. All units are Newton because the magnitude of the force is in Newton. Now we have to find out what is the value of theta x, theta y, and theta z. Okay. To find out this thing, if this one is your force vector which acts along this A to B point, then if we draw the coordinate system here, then towards this horizontal axis is x, this vertical axis is y, and this axis is z. Then the force makes angles with the horizontal axis x is actually your theta x, and with the vertical axis, that is y, it is theta y, and with respect to this z axis it is theta z. From the previous relation also we can write that the lambda, the unit vector, is equal to cos theta xi plus cos theta yj plus cos theta z k. Okay. Now you see here the value of lambda, that is this one, is given here. Okay. Now also here we can write that lambda is equal to cos theta x I plus cos theta y j plus cos theta z k. Now what is cos theta x? Cos theta is x is equal to actually the minus 0.424. What is cos theta y? It is actually plus 0.848. And what is cos theta z? It is actually 0.318. Now how we can get this theta x? Actually the value of theta x is equal to cos inverse of this minus 0.424. Theta y is equal to cos inverse 0.848, and theta z is equal to cos inverse 0.318. Okay, what we did here, that is we write this thing here. Now if we cos inverse this minus 0.424, we get this angle theta x. If we if we want to get this theta y, we can just write the cos inverse of 0.848, and in this way we find out theta x, theta y, theta z. Now you understand how we can actually calculate the angle which is made by the force in each direction, that is for the Cartesian coordinate it is theta x, theta y, and theta z. Okay, now we go to the next part of this vector algebra. It is very important topic, that is what is the dot product. Dot product is sometimes called it is scalar product, and sometimes it is called inner product. By this dot product of these two vector, any two vector, we actually get one scalar quantity. Suppose here this vector is b and this vector is a, which makes angle within them, within between them is theta. Then if we take the dot product of these two vector a and b, then it becomes AB. Here A is the magnitude of the vector A and B is the magnitude of vector B. Okay. Then if we take the dot product of these two vector A and B, then it is actually equal to the magnitude of A multiplied with magnitude of B and multiplied with cos theta. It is actually AB cos theta, and theta is the angle between them. Where the application of this dot product, or where we can apply this dot product, it is actually used to determine the angle between these two vector, any two vector. If we want to find out the angle between any two vector, we can take the dot product, and it also determines the projection of a vector with respect to another vector. Here, what is b cos theta? B cos theta is the component of this b vector along this a vector. Or if we write here, suppose we write here, it is actually, we can write that is equal to b a cos theta. Now what is this a cos theta? A cos theta is the component of this a along this b direction. Okay. So basically, how we can calculate the angle between them if the two vector is given to us? Actually, cos theta is equal to a vector sorry is actually a vector dot with b vector divided by the magnitude of these two vectors. Sometimes we write this in this form, that is mod of a into mod of b. If we divide this a vector dot with b vector with the product of the magnitude of these two vector, then we get this cos theta. And if we want to find out what is the value of theta, then it is actually the cos inverse of this thing. Okay. So basically, this dot product is a scalar product. That is why we get, if we take the dot product of any two vector, we get one scalar quantity. Now, in this case, the dot product is commutative, means the result, whatever we get, if we take the dot product with a with the vector b, the same result we get if we take the dot product with the b vector dot with a vector. Okay. And also the dot product is distributive, means if we can write this thing in this way, that a vector dot with b vector plus c vector, we can write in this way, a vector dot with b vector plus a vector dot with c vector. That is why it is distributive. Okay, you have to remind these two things. Always you have to remember this. So basically, from this dot product, we actually learn how we can determine the angle between two vectors, and the significance of this dot product is actually it determines the projection of vector with respect to another vector. Okay. Now from this equation, that is a dot with b, in place of this a and b, if we write the unit vector that is acts in x, y and z direction in Cartesian coordinate, that is I, j, k, then if we take the dot product with respect to I and also with I, we get 1, because the angle made by this two vector is 0 actually, because these two vectors, the both the vectors are in x direction. That is why the angle between these two vector is actually 0, and we know that the cos 0 is 1, and the magnitude of these two vector is 1, that because it is a unit vector. That is why the I dot I becomes 1, and if we take the I dot j or I dot k, then it becomes 0, because with respect to this I, j and k, both are the perpendicular, means 90 degree, and cos 90 is 0. That is why it becomes 0. And how we can get the result from this dot product? It is in this way. If a vector is axi, suppose ax is the coefficient of I, or we can say ax is the component of a vector along x direction. That is why it is axi. Ayj, ay is the component of a vector along y direction, and similarly it is azk. And for b vector it is bxi plus byj plus bzk. Then after taking the dot product, it becomes ax plus ax into bx plus ay into by plus az into bz. Okay, now this thing is written here, that is from this dot product a scalar quantity is obtained. Actually, if we take the dot product between two vectors, similar in similar case with the previous one, that is if this one is a u vector and this one is a v vector, and the angle between them is alpha, then it is, we can write that the u dot v is equal to mod of u plus a mod of u into mod v into cos alpha, and we can find out the cos alpha in this way. And it is already discussed that I dot I is 1, j dot j is 1, k dot k is 1, and anything else is 0, because all the I, j, k are orthogonal to each other. Okay, and if it is already discussed that if u is uxi plus uyj plus uzk, and v is another vector, what is vxi plus vyj plus vzk, then after taking the dot product, it becomes ux vx, the coefficient of I and j multiplied ux and vx plus the coefficient of j uy multiplied with the coefficient of j, that is vy, and here we take the product of this coefficient of the k in the both vector, that is uj into vj. Now what is cross product? In case of dot product we get the scalar quantity, but in case of cross product we get the another vector, and the direction of the vector is normal to the area which is containing with the two vectors. Here suppose this one is a vector and this one is b vector, and if we take the cross product, with this A and B, if we write A cross B, then we get the another vector which is A cross B and which acts perpendicular to this two vector, and it is actually perpendicular to the area which is made by these two vector. If we suppose if we consider these two vector on the two adjoining corner side of a parallelogram, then the area containing this two vector A and B is actually the length of any vector gives you the magnitude of the vector. Then if suppose this one is A, the length of this vector is mod A, and length of this vector B is mod B, then actually you have to give the vector sign here, it is missing here. Okay. Sorry. Suppose this one is A vector, sorry, this one is A vector and this one is B vector. Okay, now if this one A vector and this one is B vector, and these two vectors are the two adjoining sides of a parallelogram, then the area of this parallelogram becomes mod of B multiplied with mod of B, A mod of A multiplied with mod of B into sine theta. Because if we draw a perpendicular from this point to this point, suppose this one is perpendicular distance, means this angle is 90 degree. Okay, then and this angle is already you know that this is theta, which is angle between these two vector. Then this perpendicular length is actually B sine theta. Okay, if this one the height is B sine theta and the base is A, then the area of this parallelogram is AB. Here it is mod A, means the magnitude of A vector, into the magnitude of the B vector into sine theta. Okay, it actually represents the area of this parallelogram which is made by these two vectors. That is why it is sine theta. Okay, now after taking the cross product, we have to give the direction, because the results what we get from this cross product is a vector, and this vector is actually perpendicular to this area. Okay, whatever the area made by these two vectors. Now we have to give this direction. That is why we give here the unit vector, that this unit vector is acts normal to this area. Okay, that is why here it is written the magnitude of the cross product. The magnitude of this cross product equals to the area of the parallelogram. This thing is actually the, because if the cross product of two vector is another vector, then we can write any vector with respect to this one. If this one is the magnitude, dot with this or multiplied with this unit vector, then the magnitude of the cross product equals to the area of the parallelogram with vector A and B for sides. Okay. Now you have understand why this sine theta came here. This B sine theta is actually defines the perpendicular distance or the height of this parallelogram. Okay. And this n vector in the unit vector is actually defines the direction of the cross product. Okay. Now in case of this cross product, its direction is determined by the right hand rule. Okay. Suppose we take the dot product A vector with V vector, means A cross B, then the direction of this unit vector is this in this way. Okay. This is why it is right hand rule. If we take the A cross B, then the direction should be in upward direction. If we take the opposite thing, that is B cross A, then the direction of this C is downward, because for each time the direction of this unit vector is, for all cases, it is the outward direction with respect to whatever the area made by these two vectors. Means in previous cases, if this one is the area made by these two vectors, then the direction of the cross product, the vector which we get by taking this cross product, is obviously in outward direction. That is why in this direction. Okay. And if we take the B cross A, okay, then the area whatever we get here, the direction is in this direction, the downward direction. That is, it is actually the outward direction with respect to the area made by these two vectors. This is the right hand rule. Okay. If we take A cross B, then it is upward, and if we take the B cross A, the opposite, then it is negative in sense. That is why it is downward. That is why it is minus C. If it is positive plus C, then it is minus C. Okay. Therefore, we have to write that A vector cross with B vector is equal to minus B vector cross with A vector. It is not the multiplication sign, it is actually cross product. Okay. A vector cross with B vector is equal to minus B vector cross with A vector. Now how we can represent the cross product? We can represent this thing by determinant. Okay. If we write the A vector is AXI plus AYJ plus AZK, and B vector is BXI plus BYJ plus BZK, and if we take the cross product between these two vectors, then we can write in determinant form, that is IJK, then AX AY AJ, and here it is BX BYJ BZ. Then we can write that is AI BZ minus AZ BY I. It is for J, it is actually it is B minus J. Okay. Actually we can write this thing in this way. AY BZ minus AZ BY I plus, not plus, it is actually it is minus, actually it is minus minus of, it is for j it is ax bz ax bz minus az bx is az bx j, sorry, it is I cap plus plus it is ax by, sorry, it is ax by minus ay bx k cap. Okay, from equation this equation, that is this one, after write this equation we can write this one. If we take the minus within the bracket, then it becomes positive and this becomes positive, that is why here it is azbx minus axbz. Okay, so we can write this cross product with respect to this determinant form. Okay, now if we take the cross product with respect to I and j, ij, I cross with j, then it becomes k, because the area made by this I and j, the area of this parallelogram which is made by this ij, the perpendicular vector with this about this area of this parallelogram is k, because this ijk are the orthogonal, and the magnitude is 1 for all the ijk. That is why here if we take I cross j, then it gives you the k vector. Okay, uh, because uh, the angle between this I and j is 90 degree. If it is 90 degree, then this sine theta becomes 1, because sine 90 is 1, and the magnitude of this I and j in case of this one is 1. That is why the magnitude of this total vector is 1, and the unit vector which acts perpendicular to these two vector is k. That is why it is I cross j is equal to k. But if we take I cross k, it is minus j. Why it is minus j? You have to consider this one. Okay, I j k. Now if we go with the anti-clockwise, okay, if we go with anti-clockwise direction, then if we take the cross product with I cross j, then we get k. If we take the cross product with j with respect to k, then we get I. If we take the cross product with k with I, then we get j. All are positive. But if we take reverse direction, okay, or the clockwise direction, that is, if we take I cross with k, then it is minus j. If we take k with respect to j, k cross with j, then we get minus I. Okay, you have to remember this thing, okay, because it comes from this right hand rule. Okay, the direction of this k, whether it is upward or downward, if we take I cross with j, then we get k. If we, in positive direction, if we take j cross I in the clockwise direction, then the direction of this k is downward. That is why it is negative. We discuss it later, okay, why it is negative, in sense the direction is just opposite when we change the uh, relation here, that is whether we take I cross j or j cross I, the direction of k is opposite. Why it is opposite, in sense we discuss it later. Okay, now we discuss about the moment of a force. Now first, what is moment of a force? Basically, the moment of force is the measure of its tendency to cause a body to rotate about a specific point or axis. And how we can calculate the moment? Suppose in this case, suppose in this case we give a force in this direction by hand, then the moment about this O axis, OO axis, for this force is actually the force, the magnitude of force into the perpendicular distance from this axis to the point of application of this force. If we calculate the moment with respect to the scalar quantity, then it is force, the magnitude of force into the perpendicular distance between the axis of rotation with respect to the force application point, or the line of action of the force. But in case of vector quantity, if we want to find the moment of a force in terms of vector, then how we can do this thing? Suppose this one is the force F, and this one is the line of action of this force, and we have to calculate the moment of this force about this OO axis. Then first we have to determine a position vector between this axis and the force, line of action of this force. We have to first calculate the position vector. Suppose this one is the position vector, then if we take the dot product of this position vector with this force F, that is r cross F, then we get the moment about this axis OO, which is the direction is in this way, the moment, the direction of the moment, which is the perpendicular to the area, or the perpendicular to this two vector, that is r vector and the F vector. Then whatever we discussed earlier, that is in which direction it occurs in case of cross product, whether it is upward or downward, we see here the sense of the direction in which direction it actually occur. Suppose if we give the force in this direction, then what happened? With the help of this wrench, actually the this pipe will coming outward. Then the displacement of this pipe will occur in upward direction. But if we give the force in opposite direction, that is, suppose we give that force in this direction, then what happened? Then the direction of this moment is opposite. Okay, for this case, direction of the moment is in this direction, in the clockwise direction, and that time what happened? The displacement of this pipe will occur in downward direction. Okay, this is the sense how we can actually get this direction, whether by applying this right hand rule, whether the resultant of this not resultant is the cross product of these two vector occur in which direction. Okay. Okay, then if we give the anti-clockwise moment here, then this pipe will coming outward, and if we give the clockwise moment, then this pipe will goes downward. Okay, and this is written here, that is sense of the moment may be determined by the right hand rule. Now suppose this one is a Cartesian coordinate given here, that is x, y, z, and this I, j, k are the unit vector along this x, y, and z direction respectively. And suppose there is a force in this point which acts in this way, and the force have three component in x direction, y direction, and z direction respectively, that is fx, fy, and fz. Then if we want to calculate the moment of this force about this origin point, that is O, then first we have to uh, we have to take the position vector with respect to this O to this point, A point, and the position vector in this case is OA. In place of this R, we can write, in place of this R, we can write it is OA vector, OA position vector. Okay, because this vector is acts O to A. Otherwise we can write, or we can write it is A slash O. Okay, we can write this thing also, both are same. Now in place of R, the position vector, we can write OA, and if we want to calculate the moment about this O point, we have to take the cross product, that is R cross F. Okay, now if the force vector F is fxi plus fyj plus fzk, because fx, fy, and fz are the components in each direction, and if the R vector, that is OA vector, if we can write, if the suppose the coordinate of this origin is 0, 0, 0, and the coordinate of A point is x, y, and z, then automatically the position vector with of this A point with respect to O point, that is OA vector, is actually x2 minus x1, that is x minus 0, that is why it is xi, y2 minus 0, y2 minus y1, that is y2 is here y minus 0, that is y yj, and similarly zk. And if we take the cross product of r cross f, then we get the moment about point O. Then we can write it as the moment vector is equal to mxi plus myj plus mzk, where mx, my and mz are the component of moment about x, y and z direction respectively. And also we can write the cross product in terms of determinant, that is ijk, and here r cross f, that is why first x, y, z and then fx, fy and fz. And if we write down the determinant of this, we can write this determinant in terms of y fz minus z fy I plus z fx plus minus x fz j plus x fy minus y fx k. We can write in this way, and actually we can find out what is the moment about this O point. So here we actually learn how to calculate the moment about any point, moment of any force about any point O. If the coordinate of any point within the line of action of the force and the coordinate of the origin of the point about which we want to calculate the moment, if this two coordinate is known to us or the position vector is known to us, then we can calculate this moment about any point. Now here we did this thing again, that is here we can write it is r position vector r, that is a slash b, or otherwise we can write it is, or we can write it is, here we can write this thing as r b a. Okay, that is written here. We can write this thing r cross f. If the coordinate here for b point is x a comma y a comma z a, and the coordinate of, sorry, for b point it is x b y b and z b, and for a point it is x a y a and z a, then we can write the position vector, that is x a minus x b, because this a point is the final point, x a minus x b I plus y a minus y b j plus z a minus z b k. And we can write the position, the force vector in terms of fx I plus fy j plus fz k. Then we can actually write this determinant form. Okay, actually we discussed this thing in our earlier slide. Okay, now if we want to calculate the moment of a force about any given axis, okay, suppose first this one is the force vector f, and we want to calculate the moment about this O point, then first we have to take the position vector, which is from O to this line of action of this force, that is r here. And if we take the moment about this O point, it is, we get this mu in this direction, that is perpendicular to this r and f both. Then if we want to find out the moment of this force f about this line instead of this point O, if we want to find out what is the moment of this force about this axis, about this given line or axis, that is OL, then what we can do? First, we have to calculate the moment about O, okay, that is R cross F. Then we have to take the dot product of this moment with the unit vector which acts along this OL line. Okay, this lambda is actually the unit vector. It is actually the unit vector unit vector along OL. Okay, it is actually the unit vector along OL. If we take the dot product of this unit vector with this moment, then actually we get the moment of this force F along this given axis or about this given axis, that is OL. Actually we get the component of this MO along this line. That is why it is scalar quantity, because here we take the dot product. Actually we get the component of this MO along this OL. That is why we take here the dot product, because actually this dot product is the component along the another vector. Here we take the unit vector, because unit vector have no magnitude. The magnitude not no magnitude. It's having the magnitude 1 unit vector. That is why it doesn't multiply any number with respect to this moment. It actually shows the direction of this OL line. That is why if we take the dot product with respect to this moment, then we actually get the component of this MO along this OL line. Okay, now suppose here, suppose we draw a force here. Okay, suppose this one is the force F. Okay, and suppose here one point P is defined within the line of action of this force, and if we want to find out the moment of this force about this point, suppose Q, then first how we can do this thing? First we have to take a position vector, here. Okay, suppose this one is the position vector, then how we can write the notation of this position vector? It is actually R Q P. Okay, or otherwise we can write R P slash Q. Okay, then what is the moment about Q? M Q is equal to this R Q P cross F vector. If the coordinate of P and Q is known to us, that is, suppose the coordinate of P is x2, y2, z2, comma x2, comma y2, comma z2, and the coordinate of xq is equal to x1, comma y1, comma z1, then rqp, that is the position vector of P point with respect to this Q point, is actually x2 minus x1I plus y2 minus y1j plus z2 minus z1k. Okay, and if we take the cross product of this position vector with this force vector, then we get the moment about this Q point. Now suppose here we want the, suppose here there is a line, okay, line, and this point is suppose N, and if you want to find out the moment of this force F with respect to or about to this qn line, then the moment about this qn is equal to unit vector along this qn dot with mq. Okay, and this mq is equal to rqp cross with f vector. Then you get the component of this mq along this qn line. Okay, I think you have understood how to calculate this moment about a point or about a line. Now what we actually learned today. First, we learn how to represent a force vector in terms of this cos theta I, cos theta j, and cos theta k, where this cos theta x and this theta x, theta y, and theta z are actually the angle made by this force component, force along about the x, y, and z direction. Okay, suppose here it is, draw Cartesian coordinate here. Okay, suppose this one is x, this one is y, and this one is z. Then if a force acts in this way, okay, force acts in this way, then this angle is theta x, this angle is theta y, and this angle is theta z. Okay, and also we can write the force vector, that is force vector is equal to magnitude of the total force F, and lambda is the unit vector along the direction in which force acts. And we also learn what is the dot product and why this dot product we consider or we take this dot product. And the value of this dot product is actually a dot b it is a scalar quantity when we take the dot product of two vector, and it is ab cos theta, and theta is the angle between these two vectors. And um, how we can calculate this dot product, it is given here, and this equation is applicable to find out the angle between these two vectors. And here for the cross product, that is a cross b is equal to c, which the value or the magnitude of the c is a vector mod a into mod b into sine theta. It is actually the area of the parallelogram which is created by these two vector, and this n is the unit vector along which direction this cross product is actually acts. And how we can calculate this cross product in terms of this determinant we learn. And also we learn how to calculate the moment of any force about any axis or any point or about any given axis. Okay, we actually learn this thing. Okay, this is uh, for today's lecture, and in our next lecture we learn how to solve the different numerical problems regarding this vector. I think you have enjoyed today's lecture. Okay, thank you.